Over the last few months, we've spent a lot of time improving the performance and visuals of the dynamic game world. But the horizon all around it looks quite monotonous here, with ocean as far as the eye can see. Wouldn't it be nice if we could spruce it up a bit? Today, we are procedurally manipulating a single mountain mesh with a rectangular footprint to form concentric rings of variable peaks around our world. Doing this on the main thread takes around 150 milliseconds, which isn't a problem for a once-off occurrence. However, in the interest of keeping every part of the game performant and developing technology that can be used later on, we'll use burst compile jobs to edit the mesh data directly in parallel. First, we'll warp the footprint into a curve forming part of a ring. Then we'll add both overall and local variation in position and elevation. We'll also flip the mesh over on either or both the X and Z axes to vary its orientation. Finally, we'll arrange the meshes into concentric rings, with each ring producing increasingly larger peaks to give the horizon some depth. Let's consider each of these steps in a bit more detail before we implement it in parallel. First off, we place a number of peaks around the game world by choosing a radius and using simple sine and cosine calculations for the X and Z coordinates. I've chosen 6 peaks per ring, so each one fills an arc of 60 degrees. We now need to convert the Cartesian coordinates of each vertex in the rectangular footprint into the radius and angle in its polar coordinates. If we express x and z as proportions of the total width and length of the footprint, we can transpose x onto the radius and z onto the angle sweeping out the arc. This turns the rectangular footprint into an arc lying on a circle around the midpoint of the game world, and the 6 meshes together complete the circle. Then we add some randomness to the arc and radius of each mesh to scatter them around slightly. We give each mesh a random elevation multiplier and also look up a noise value to apply to the elevation of each vertex. This produces considerable variety in the meshes, even though they originate from the same source. We can go one step further and flip a mesh on either or both of the axes. We simply use 1 minus the proportion in the calculations. If a mesh is flipped along an odd number of axes, we also need to reverse the order of its triangles to get them facing outward again. Here's the code to accomplish all of this. We won't work through it in detail, but it's simple enough, especially with the visualizations we've just gone through. Let's rather focus on how to adapt this so that it can run in parallel. Running this on the main thread only, we see that it takes slightly more than 150 milliseconds to complete. However, Unity provides an advanced mesh API that allows us to allocate writable native memory for mesh data, which we can then fill from jobs. While we still need to create the game objects and components on the main thread, we can move the calculation of vertices, UVs, normals, triangles, and bounds into parallel jobs, and create the objects while these are running. Our first step is to allocate memory for the mesh data. In this case, we ask for 18 sets of mesh data, 3 rings with 6 meshes each. Each of them needs the same amount of memory, since they will contain the same number of vertices, just moved around differently. So, we create a vertex attribute layout, indicating that the mesh will store positions, normals, and UVs for the vertices. Then, for each mesh, we set the buffer parameters for the vertices and the triangle indices. Using the attribute layout and the number of vertices, the correct amount of native memory can then be allocated. To populate this memory, we create one job for each mesh, supplying each job with the source mesh data, its randomization parameters, and importantly, a pointer to the memory allocated for that mesh. We schedule each job as we create it, so they can all run in parallel. Each job obtains pointers to the native memory for positions, normals, UVs, and triangles, and then performs the actions we've already discussed to transform and randomize the mesh. But we also calculate the bounds and normals in the job, so that we don't have to perform the standard recalculate bounds and recalculate normals calls on the main thread. Once all jobs have been scheduled, we perform the actions that absolutely need to run on the main thread, creating the game objects and adding the components required to render the meshes. If the jobs haven't completed by this point, we wait for them to finish, then set the bounds for each mesh to what has been calculated in the jobs. We can now simply apply the 18 sets of mesh data to the 18 meshes and dispose all the temporary memory used. So, how much faster does this run when threaded? You can see here that the time is fairly volatile depending on what else is running in the game, but it's generally between 10 and 20 milliseconds, which means we can run it roughly 10 times in the time it used to take to run it once on the main thread. And note that we're recreating both the jobs and the game objects every time we run it. In cases where we'd truly need to update meshes frequently, we'd keep the jobs and objects in memory and just update them each time. And that's how we create procedural meshes with burst compiled jobs. Please like if you enjoyed the video, leave a comment, subscribe to this channel, wishlist and follow Minor Deity on Steam, or join the Discord server to stay up to date. All the links are down below. Also, feel free to ask specific questions you may have. Thanks for your time and support.